Hi dear, today we'll see the image formation by concave lens. Okay, so we'll represent that image by the using the ray diagram, right? So we are having some certain rules to draw the ray diagram. When it is refracted to the concave lens, how it will emerge out. Okay, so we have three rules to make the ray diagram. Okay, by the like convex lens, for concave lens also we have three rules. Okay, let's see one by one. First one is a ray of light parallel to the principal axis. Okay, when a ray of light parallel to the principal axis appear to diverge from the focus located on the same side of the lens. Okay, appear to diverge from the focus located on the same side of the lens. This is very important. Okay, so when the ray of light, how the light incident on the lens, it is parallel to the principal axis. This is your principal axis. When it is parallel to the principal axis, okay, when it is parallel to the principal axis, appears to diverge from the focus located on the same side. So same side of the focus point is f1. It appears to diverge from the focus. See, it appears to diverge from the focus. This is how it will be diverge. Okay, it appears to diverge. So you have to mention this with the dotted line. It appears to diverge from the focus. Clear? So when it is parallel to the principal axis, it appears to diverge, because it is a diverging lens. It appears to diverge from where? If you look at from here, look at from here, it appears to diverge from the focus. Okay, so this is the first rule. If a ray of light parallel to the principal axis appear to diverge from the focus located on the same side of the lens. Okay, if you look at this diverge light rays, it actually appears to come from this focus point. Okay, this is the first rule. Okay, next one, a ray of light appears to meet the focus. A ray of light appears, I am using the word appear. Actually it is not meeting the focus. Okay, in the first rule also it appears to diverge. Okay, likewise here, a ray of light appears to meet the focus, will emerge parallel to the principal axis. See, for example here, it appears to meet at the focus. So the light rays appears to meet at this focus. Okay, so that means it will be coming like this. It appears to meet at the focus, will emerge out parallel to the principal axis. This is your principal axis and it will be parallel to the principal axis. Okay, when a ray of light appears to, it is not actually meeting at the focus point, it appears to meet at the focus, it will emerge out parallel to the principal axis. This is parallel to the principal axis. Okay, this is the second rule. Okay, next, third one is same for in both convex lens and concave lens. So ray of light passing through the optical center will pass without any deviation. There is no deviation. Okay, so this is your optical center. When the light rays pass through this without any deviation, it will goes like this. So without any deviation it will go like this. See, okay, that's all. So the three rules are: when it is parallel to the principal axis, it appears to diverge from the focus point on the same side of the lens. When it is appears to meet at the focus point, then it will emerge out parallel to the principal axis. And when it is passed through the optical center, there is no deviation. Okay, these are the three rules to be followed while drawing the image formation by the concave lens. Okay, so first here only two position of the object. Okay, at infinity and between infinity and the optical center. These are the two positions of the object. So we'll see how the image is formed, where the image is formed. Okay, when infinity. If the object is placed at the infinity, the rays will be parallel to the principal axis. You know that, right? So the rays will be parallel to the principal axis. Okay. We need at least two rays to get an image, right? The meeting point of that image will give rays will give the image, position of the image. Okay, so these rays are coming from the infinity. Okay, so it is parallel to the principal. This is parallel to the principal axis. Both are parallel to the principal axis. What is the rule? When it is parallel to the principal axis, it appears to diverge from the focus on the same side, right? So that means it appears to diverge from here. Okay, right? Okay, so here also it appears to diverge from here. Clear? When a ray of light parallel to the principal axis, it will appear to diverge from the focus on the same side of the lens. Clear? Okay, so if you see these refracted rays, it is diverging, it will never meet. So it appears to meet at this point. It appears to meet at this point. So you will get the image at F1. Clear? You will get the image at F1. So the position of the image is at F1. What is the nature of this? This is virtual and erect, because actually the rays are not converging, and you will not get the image at that point. It actually appears to converge. Okay, so you will get only the virtual image. Okay, that too erect. Okay, this is point sized. What is the size of the image? Point size. Clear? When the object is kept at infinity, you will get the position of the image at the same side of the lens, that is virtual and erect, at F1. Okay, point sized image. Your next position is when the object is placed between infinity and the optical center. Okay, somewhere between the optical center and the infinity. Okay, so I have drawn the line up to here, C1. Let's take here. Okay, so this is your object. Okay, so we need at least two rays to get an image, right? So one, it is parallel to the principal axis. You know that when it is parallel to the principal axis, it appears to diverge from the focus point, right? This is how it will be diverged. Okay, it appears to diverge from the focus point. Okay, we'll take another one. This is optical center. So when the ray is passing through the optical center, there is no diversion, right? Without diversion, without diversion, it will go, right? It will go. Okay, so where is the meeting point of these two? So these two rays will never meet, because both are diverging. Okay, so these two lines appear to meet at this point. See, this ray will appear to meet at this point. These two rays will appear to meet at this point. So this is your image. Here your image is formed. Okay, so where the image is formed, it is between the optical center O and the F1. Okay, focus point. So what is the nature of the image? Virtual, because it is not actually, the rays are not converging and you are getting image. No, it is not converging, actually it is diverging. So we are taking that it appears to converge here, meet here. So you will get the virtual and erect image, that is diminished in size, small in size when compared to the object. Okay, these are the image formation by the concave lens when it is at infinity, and when it is between infinity and the optical center, we get the image at F1 and O, and in both the cases you will get a virtual and erect image, and at infinity means you will get a point sized image, and between infinity and optical center means you will get a diminished image. Okay, these are the two images formed by the convex lens. And next one is sign convention. So you know that how we use the sign convention for the spherical mirror. Same thing is applicable for the spherical lens also. Okay, quickly we'll do this. So for this convex lens, this is concave lens, distance of the object. You know the distance of the object means object is always kept on the negative side of the x-axis, right? We'll use the coordinate system, right? Here both are for y and x, it is both are positive. Here this negative, here this is negative x-axis, so negative. For y it is positive only. Here both are negative, and here in this quadrant x-axis is positive and y-axis is negative. Okay, same convention. So object, distance of the object. So for both the cases, convex and concave lens, the object is kept at the left side of the x-axis, negative side of the x-axis. So it is negative. Always make sure negative, right? This is also negative. Okay, distance of the real image. In the concave lens, just now we got only the virtual and erect image, so it is not applicable. In the convex lens, you remember that you will get the real and inverted image in the other side of the lens, that is positive x-axis. Okay, right side of this y-axis, that means here in the positive side of the x-axis. So it is always positive. Distance is measured positive. Okay, distance of the virtual image, in both the cases it is negative, because virtual image will form on the same side of the lens in the concave lens, just now we have seen. And when it is kept, object is kept between sorry if the object is kept between the focus and the optical center, you will get the virtual image. Okay, that will fall in the same side of the lens, right? So that is also negative. Next, focal length. Focal length, when the object is kept at the infinity, you will get the image at focus, right? So then it is positive for the convex lens. Okay, just now we are saying for concave lens it is negative, because it falls on the same side of the, it appears to converge at the focus on the same side of the lens. Okay, so it is negative. Then height of the object. So height of the object is always kept above the x-axis, so it is positive. So both the height of the object is positive. Okay, height of the real inverted image, this is not applicable for this concave lens, because we will get only the virtual image. Height of the real and inverted means it is below the x-axis, right? So it will be negative. Then height of the virtual erect image. Virtual erect image means always it is positive. Your height will be kept above the x-axis, so it is always positive. These are the sign conventions used in the spherical lenses while calculating the while doing the numericals. Okay, so that's all with this. I'll see the lens formula and some few numericals in the next class. Okay, thank you.